Okay, we're back with the second half of this lab on AC to DC. This is part 2 of the first of the rectifier labs, and we're going to be looking at, as I have on the screen here, the full wave bridge. So let me move the camera, get some things set up, and we'll do this part of the. Okay, so I'm going to bring up the scope again. This is kind of where we left it. And I want to show one change when we get to measuring, one change from your diagram. I moved this V source, you have it over here. I moved it back here to this source voltage. And the reason for that was because when we try to display the two signals, source and output together, the common ground here actually shorts out this diode and the other diode alternately. I'm sorry, these two diodes. So when you see it on the scope, you're actually going to be seeing this one right here. Okay, so let me, here is that waveform. So I've now just moved here's the input, and I've got the signal trace right here. This is the blue line that you're seeing. Okay, a nice perfect sine wave. Now we know it got multiplied when it came through here, so what's going to come out the other side is going to be a little bit bigger. So I'm going to show you some of that. All right, and as we right now all you're seeing is the input trace, the blue line. Right now I have no load on it, no 100K and no 10 microfarad. So I'm just going to measure the output voltage here by putting on, I have a ground, this is ground all along the bottom of the board. So I have a ground to there, and I've grounded this point. That's this little piece right here. I made that as this black wire. I'll hold this up for a moment, hopefully the things don't all fall off. A little hard to see, actually, the diamond. Wow, that's too bad. I had to get such small resistors, diodes here. Let me see if this will help. No, the lighting is not good enough that you can maybe if I shadow it here a little bit. No, it's not really showing, but you'll have to. You can sort of see three black. Here's one side of the diamond, here's another side of the diamond, and there's the other. So the diamond is right there. And if I measure on this side of the diamond, notice the red line that popped up. So what I actually just did was put a measurement, whoops, I'll show it on the diagram. I put a measurement from here, the red trace is showing from here on the diagram to over here. And I have no load on it. Okay, so you're seeing absolutely full wave rectification right here. This trace is the flip up of the bottom trace. And very little offset from zero. Okay, actually it's because I have it set on DC. So, and with 5 volts, you're seeing here, well over 3 volts. The difference between 5 and 3 and 3 plus is 2 diode drops. 0.7 plus 0.7 is about 1.4. So if I look at this number, it's really 3.7. See, it's really right up there, about 2 diode drops away. That would be the case if this signal right here was actually 5 volts, which it is. We just can't show it simultaneously on the scope. Okay, now if I plug in the 100 ohm resistor, we're going to see if anything happens here. So I'm got these fine lead resistors, and they always want to pull out. So now I just put on the 100 ohms, and I clip back on, and it dropped a little bit maybe, but no, not much. the shape is still the same. You see a lot more definition down here, zero definition, where the diodes have to turn off and turn on. So the switch gets made. So you actually get to see some of that down there now, which is good. So that's full wave rectification, kind of at its best. Now we can measure we can measure the RMS value. We got to use the multimeter for that. And we can measure DC values. And we're talking about now without the 10 microfarad on there, right? Let me show you. I'm going to pop it on and off. I've got a 10 microfarad capacitor. Let me show you what happens when I do that. Look at it. It creates a nice flat DC value at, what, 2.8 volts, something like that. Nice and flat, though. Very well regulated. No, well, it's not regulated, but very well, contained. The quality of that straight line, red line, will change depending upon the amount of the load, the 100K or less, and the size of the capacitor. We make that smoothness by putting on a big capacitor relative to the time frame. So before we check all that out, let me talk about this, the source voltage measure. So I'm going to measure now the one that you have shown on your diagram. This is really the source we're talking about. And I'll do it in RMS, so I'll turn on our meter. And it comes up to AC directly. So I'm just going to measure the source here. It's on the outside. What's going on? Oops, I'm on DC. That's what's going on. Okay, I needed to switch it to AC. All right, and I get 2.976 volts AC. That's AC RMS. Okay? So that's the RMS value right across here. Now if I measure the, what else do we want? We want DC of the output voltage. So now we'll go back to DC. So that was the blue that I measured. Now I'm going to measure the red. And it's going to be, what do we get? On DC, looks like it popped in there for a moment. We don't get much. DC. No, because it's still pretty much an AC looking voltage, right? So kind of zero. Because it's time varying, right? And the meter is looking for something that's pretty steady. So now let's actually complete the circuit. That's the number they want, the number that is supposed to go in here. I'll measure with the multimeter, but it's after I put this on. So you notice you don't really get DC the way it looks now. You don't get DC until I do this. Put this on in the right direction. Okay, so there's that. I'll move this aside so I can get it hooked in. Okay, now we'll try again measuring DC and see what we get. So here I am on one side of it, here I am on the other, and I see 2.8 volts. 2.8 volts DC. And that is just roughly the same as this. This is 2 volts, below 3 volts, so that's about 2.8 volts. Let's just check. Oh, 272. I guess if I put the probe in exactly the right spot, 275. So that's about 2.8. Okay, so this is a real nice measurement, a real nice provider of good DC current. And this is the exact circuit in your wall warts. The 100K is not there. The capacitor is there. Remember from the lecture picture, the capacitor is there, the bridge is there, the transformer is there, and the plug is there. The 100K is whatever you plug into it, your iPhone, your stereo, this or that, okay? So the picture that I would like you to sketch, well, you can do this one, right? But the picture I really want you to sketch is this one. The full wave rectification. That's what you should be sketching down here. And the division marks are 2 milliseconds per division on the horizontal, and then you can mark the vertical divisions to be what they what they are here, or you can just mark what we measured is fine. Okay, so that's all I'm going to say about this lab. I really wanted you to see this picture, how beautiful, and then when you add the capacitor to it, how smooth that output becomes. So this will be it for this lab. We're going to do one more rectifier lab, full wave, but we're going to do that as a second demo lab, and that will be the center tapped transformer. So we'll take this transformer and flip it around the other way. So it's going to be kind of, I may have to switch the power supply because it's going to be kind of low voltage when we do that, but I'll see when we do it. All right.